There are a few properties of logarithms we need to know very well. And the thing is, some of those properties work one way, but if you change them, change a little operation, then the properties don't work the same way. And it's very easy to get them mixed up. We have to know exactly how the properties work. Because again, it's very easy to change one operation in the equations, and then the properties don't work anymore. And part of what we are doing as students is getting to know those nuances, those little details, those little changes. They are a big deal in mathematics. We magnify the difference between one operation versus another operation. Let me start with one of the properties that is very, very important. So we have that, let's put a bullet here. The logarithm in any base b of the product of two quantities is equal to the logarithm in the same base of 1 plus the logarithm on the same base of the second factor. So we got two things that are multiplying, and then that is the sum. First of all, make sure you know how this works in the sense of get to know what operations are being used. It's very easy to change this around and end up with a wrong conclusion. Okay, so I'm going to box it. This is very, very important. Don't neglect to know this. And there's more than meets the eye. When we write this down, we're not only saying that this is true every time that we can plug in numbers into those logarithms. We're also saying that other things are not true. This tells us not only what we can do, but what we cannot do. So again, I'm going to repeat that because that is very important. Many times, an equation in mathematics tells us what we can do, and beyond that, it tells us what we cannot do. For example, we don't have a property that says what we can do with that. That has no simplifying. Okay, so this can't be simplified. If you twist it around, if you force a factoring, for instance, if you factor the a out and then you end up with 1 plus the quantity b over a, then yeah, you can apply that. But in general terms, keeping the addition as is, we cannot do that. So be aware. Quite often, an equation tells us what we are able to do, and implicitly, it tells us what we cannot do. Let me give you an example that has not really much to do with logarithms. It's a different example. So for instance, you have ab squared, and we can distribute this square with no problem. That is okay. But if we have the addition and we square that, we cannot simply distribute the exponent. That is not okay, comma, not okay, not okay. So even though they don't tell us that explicitly oftentimes, although many teachers do, they get out of the way to actually show students that this is not what we are supposed to do. Only this or things that are similar to that are okay. In other words, exponents work really well with multiplications or divisions. Exponents don't work as friendly with additions or subtractions because then we have to FOIL out. Similarly here, logarithms work really well with multiplications, divisions, and exponents. That's one of the things we're going to be doing in this video, working with multiplications, divisions, and exponents, which are roots, can also be seen as exponents. And they can be broken up into simpler logarithms. Yes. In fact, there's a historical um, application of this in 50 years ago or so, 60, somewhere in that neighborhood of time. Um, Calculators, uh, electronic calculators, the ones we use, um, were not that popular, were not available. So people still have to figure out logarithms um, in those days, and actually multiplications, large multiplications. If you need to perform a large multiplication, a simple calculator like this one will do. Um, but in the old days, 50, 60, 70 years ago, multiplications were a big deal. Just multiplying to big numbers, 5, 6 digit numbers were a big deal. And this actually helped out a little bit to do that. Um, yeah, so logarithms have this property. Do not try to do something else. Make sure you figure this out. Oh, and the other thing that could be a problem is logarithm in base b of ab is definitely not equal to the logarithm in base b of a times um, the logarithm in base b of big B. Again, that is not true. Well, if there was an equation, that wouldn't be true. That's what I'm trying to say. Those two quantities are not the same. The only way we can break up a multiplication is by addition. That's the only way we can do that. So please don't take this too lightly. It is, and the reason why we shouldn't take it too lightly is because it only works in a certain way. It doesn't work in other ways, such as that or that. It doesn't work, a multiplication doesn't break up into a multiplication. And if we have an addition, we cannot break that up anyway, in any way, form, or shape. It will be kind of easy to put together problems for assessments, quizzes or tests where we try to, uh, the, we're not necessarily trying to trick students, but we are testing many times whether they know the properties and whether certain things cannot be applied. So some questions we ask in assessments are not meant for the student to be tricked. They're meant to test precisely whether the student knows how the properties work and how the properties don't work also. Let me give a short explanation of how this formula comes about. So if you have b um, to the logarithm in base b of a and multiplied by, again, b logarithm base b of b, there are two ways to think of this. On one hand, the logarithms cancel off and exponents go before multiplication. So this is, on one hand, this is equal to, well, those two simplify and we end up with a. Yep, those two simplify, so we are multiplying with b, and that can be thought of as the logarithm in base b. Oh, I'm sorry, not the logarithm. I meant to say b um, to that logarithm that I was going to write down. So let me erase this very quickly. Okay, b to the logarithm in base b of a b. Okay, on the other hand, it can be thought of as b, when you have the same base and exponents and you multiply those two quantities, what do we do with the exponents? If you have, for instance, a to the 3 times a to the 4, I'm changing the bases. So again, if you had little a to the 3 times little a to the 4, what we do is add the exponents and we end up with a to the 7. Well, likewise here, since we have the same base, we can simply add the exponents. So this is the logarithm equals the logarithm in base b of a plus the logarithm in base b of b. I'm not putting parentheses just so that I don't have too much going on the exponents. So this exponent, this quantity rather, is equal to this quantity with the same base, and that big, huge exponent. All of that is the exponent of that little b. Here, that is also the exponent of that little b, and this quantity is equal to that. By the transitivity of equations or equality, that means that this guy, or that exponent, well, this quantity is equal to that quantity, and that means that the exponents have to be the same. And that explains this. So logarithm base b of a product is equal to the logarithm base b of a plus the logarithm base b of b. Well, anyway, the bottom line is make sure you know that property. Very, very important property. It only works one way. And the best way to learn properties is to do loads of homework, tons and tons of homework. I have had students who tell me, I'm not very good in math, and somehow they know they should do a lot of homework, and they end up performing quite well. So on the other hand, I've seen students who appear on the surface to be very, very fast at getting to know things, and they get overconfident. They don't do enough homework, and they end up performing not as good as expected. So what I have learned over the years is not to assume anything. Who performs well is unknown to me until they perform. I don't know. I cannot judge ahead of time until, and even sometimes after an assessment is graded, we don't know necessarily because mistakes can happen. Anyway, so that is one property. The other property that is derived from this, okay, so if a product under a logarithm is the sum of the logarithms of the factors, that means that a quotient is a subtraction. If we divide, then that translates here into a subtraction. So the logarithm in any base of a over b is equal to not the quotient. That is very tempting. I almost wanted to put logarithm of a over logarithm of b, but that is completely incorrect. So logarithm base b of a, take away the logarithm base b of big B. Okay. So again, make sure you know that property. It's very, very easy to get that confused. I almost wanted to write down the wrong thing, which would be the logarithm a over the logarithm b. So that is a second property. I put a bullet. A third property, which is also very, very important, is that the logarithm in any base of a to any exponent, the exponent has to be on the thing that we are taking the logarithm of, can be rewritten as r times the logarithm in base b of a. Okay. One thing that I see students getting confused with when we are dealing with logarithms is that numbers get to be written in a very, very complicated way. But don't be afraid. They're still numbers. They're just numbers like any other number. So let me make a note of that. Okay, so note that logarithms are just numbers. There's nothing weird. See, this is what I mean to say. Let me give you some examples of numbers. So some numbers like 3 are easy to think about, and you can add, because we saw those numbers, all the time since we were in elementary school, since we were very young, and we know how to handle that, of course. And then as we move on, we get into more complicated numbers such as 3 pi, and then 4 pi. And then what is that equal to? Well, that is 7 pi. And at first, maybe that is a little confusing because it's like, wait a minute, 3 pi, what is that? Am I supposed to multiply 3.14? No. Times 3, and then multiply 3.14 times 4, and then put it in a calculator. We get, no. What we want to do is just simply treating them as regular numbers. Okay, and then we also have more complicated numbers because we have numbers within numbers. So let's say you have 3 times the square root of 5 plus 3 times the square root of 5 again. Oh, I meant to say 4. I want to stay consistent. And this eraser sometimes is slower, and then I get all nervous because, and then it's not performing as good as it should because I'm in front of the camera. Anyway, 4, 5 here. All right. Okay, so this is really confusing at first because, hey, there's a 5. Do I put 10? 5 plus 5 is 10. I know that there's an addition. No. We gotta watch out. This behaves exactly the same thing, the same way as the pi's. We didn't say, oh, 7 times 2 pi. And we didn't certainly say 7 times pi squared. There's many ways we could have gone with this. And we, over time, learned how to handle that and not to be so afraid of the pi's, getting too nervous about how to handle them. And by the way, this gets more complicated because there's more than one operation. If you have 3 times 4, that is 12. If we have 3 pi times 4 pi, of course, that is 12 pi. But then we got to square it because then the pi's multiply out. And then you may be thinking, hey, wait a minute, do we do 3 pi times 4 and then 3 pi times pi? No, because we don't distribute. So that is an additional complication if we have addition along with multiplication on the same expression. Then we may have to use the distributive property. There's a lot of little nuances about algebra. Having said that, once you get to know those few nuances, then you're set. You're set pretty much for life. Students who get to know the algebra properties early on, believe me, that takes you all the way out to it's used for a long time if you keep taking more mathematics. Same thing here. Yeah, and then this gets even far more complicated because if we were to multiply this 3 times the square root of 5 times 4 times the square root of 5, that's going to be 12, but then the square root of 5 is multiply out just like the pi squared, but then that gives us 5 times the 12, so we end up with 60. Okay, so now we got logarithms. Something like logarithm in base 2 of 3 plus a logarithm in base 2 of 4. Okay, so this has a special rule of its own. Those have special rules also. We just are way more familiar with them. We may be a little shaky about some of the rules perhaps, but we are, for the most part, very familiar with those rules. This one has a new rule, and we have to get to know it. If we don't do well in the logarithm section, it is not necessarily because we're not smart enough. It isn't possibly because we simply don't have the rules at hand. We don't react quickly to what we're supposed to do. So first of all, when we have an addition of logarithms, we can use this equation, this property going backwards. So the addition of 2 logarithms with the same base is really the logarithm in the same base of the product of the 2 inputs. So using that, this is equal to the logarithm in base 2 of 12, which is unexpected. Here we did that addition and we got 7, again 7. Oh, I didn't finish this guy. That is 7 times the square root of 5. Okay, and I don't want to confuse those two. All right, but here we don't get the logarithm base 3 of 7, or base 2 rather, of 7. We get logarithm base 2 of 12. That's a different rule we are applying, and we have to know it. We have to learn it. I don't know. In my opinion, it is very difficult to think this out without practicing, without learning it, without somebody telling us what to do. Can we figure it out on our own, maybe, but we don't have enough time to do that. At least most of us don't have the time. So we have to be told how to do this and then work through the problems and learn it very quickly. But the same thing happens with any skill. You know, if you are in construction and you're trying to put a wall, you know, a frame for a wall, you know, there are certain things that you do and how to do them properly. Can you figure them out on your own? Yeah, sure, you could, but if a master carpenter comes along and tells you, no, you got to do it this way or this other way, because otherwise, you know, things will fall apart, or they won't be as square as they could be. Then we just learn it, and that's kind of how this goes. So watch out for this expression. Practice it. Go over it, especially with the homework. That's one of the reasons why we have the homework. By the way, if we multiply the two logarithms, so say you have the logarithm base 2 of 3 multiplied with the logarithm base 2 of 4, there is no property that allows us to put this together into one logarithm. We're stuck with a product. Okay, so we can't put them together as one logarithm, as one simple logarithm. Yes, so if in a book you see a section about properties of logarithms, you may be a little silly to go over the homework, because the homework is just the application, and you may be thinking, well, that doesn't seem too difficult. You know, I'm just applying the formulas. Yes, but what we're trying to do with that is getting to know them. Some people may say, well, what is the point of that? I can always look up the formulas, you know, on the internet or in a book, you know, whenever I need them. It actually slows the process down. If we don't know something, if something is not available, you know, right away when we recall it, then the whole process becomes very, very slow. Yeah, excessively slow, inefficiently slow. Yeah, I was going to repeat excessively again. Yeah, it is not good. Yeah, let's say, just to give you a quick silly example, perhaps, say I wanted to do I don't know, 47 plus 92, you know, and then 7 plus 2, let's pretend I don't know that by heart, and I have to do, okay, 7, 1, 2, 3, 4, 5, 6, 7, and then 2 more, 8, 9. So if I did that long addition, which is not that long, you know, by complete fingers, because I know somebody could say, well, I know the concept, and I can, you know, I just use my fingers and do it. That's fine. There's nothing wrong with that, except that if we do more and more additions, that slows us down dramatically, you know. And then 4 times 4 plus 9, so that's 9, and I need more fingers. So, you know, it does slow us down. It's better to just memorize, you know, 4 plus 9 is 13, and then just write it down and just move on. Same thing happens with logarithms. When we start working on equations and expressions, do you have the time of the luxury of time to slow down? Perhaps you do, but it then becomes too excessive, too long. Let me talk a little more about the third property. Let me write it again. So the logarithm in base b of this to a power is equal to logarithm base b to a. Oh, but I now remember what I was doing here. So when you see the logarithm, that's what I was, logarithm base 2 of 3, don't be afraid of this. This is just a number. What number is it? I don't know. I mean, I kind of do. It's a number, you know, we want an exponent. So that 2 to that exponent is 3. So that exponent has to be somewhere between 1 and 2, because 2 to the 1 is 2, 2 to the 2 squared is 4, and 3 is in between those two. So somewhere in between, we got that number. you know, what is the square root of 5? I don't know, it's 2 point something, because 2 squared is 4, 3 squared is 9, 5 is in between 4 and 9, so the answer has to be between 2 and 3. And likewise, the answer here has to be between 1 and 2. But what I'm trying to tell you, though, is don't be afraid of this. This is just a number. Okay, so before I move on with this, if you have the logarithm in base 7 of 52, I'm just making this up. This is just a number, the same kind of number as if it was just 8. I'm not saying it is equal to 8. Those two are just numbers, you know, or 8.42. That's just a number. Don't be afraid of it. It's just like an 8 or like a 2. That's a number. Um, and that's a 52, by the way. It is not, there's a little bit of a gap in between, but that is 52, not 5 space 2. It's 52. Let's say you have 375 over 915. That's just a number. Don't be afraid of it. It's just a number. It looks weird because it isn't. Actually, that can be simplified because both are divisible by 5. But anyway, beyond simplifying, this is a number. And then there's numbers that look really weird, such as 3 plus the square root of 2 over 4 plus the square root of 5, for example. Again, that's just a number. You know, you can plug it into your calculator and it gives you a decimal. Same thing with that. You can plug it into your calculator, although you have to use the change of base formula because calculators usually have logarithms in base 10, and in base E, they don't have logarithm in base 2. Nonetheless, it is just a number. So please don't be afraid of those weird expressions. They're just numbers. So the reason why I'm bringing that up with this particular property is because what we are doing is changing this exponent into a product. We're multiplying R with this one single number that we should not be afraid of or be intimidated by. This is just a number, nothing else. Okay, so how do we apply that? And let's start working out some examples. For instance, the logarithm in base 2 of the square root of 5 is equal to, let's see. Well, first, think of the square root as an exponent. So this is the logarithm in base 2 of 5 to the 1/2. Square root is the same thing as the exponent, 1/2, which is in turn equal, using this property, the exponent multiplied with the logarithm. Now, we typically put the exponent first. I forgot to put it here first, so that's why I put it after. And the reason why we do that before is because otherwise, somebody could read this ambiguously or incorrectly. The logarithm base b of a is what we want, and then whatever that is multiplied with r, somebody could misread this as logarithm base b of a times r. So in other words, multiply those two and then find the logarithm of it. So we got to be careful. To avoid confusions or ambiguities altogether, we usually put the 1/2 first. So that is the exponent, that is like the r, and then multiplied with the logarithm in base 2 of 5. There we go. So whatever this is a number. We're going to multiply it with 1/2. Let's do a few more examples. This is going to be a longer example. So assume, okay, logarithm, let's just put the logarithm in base 10 of 2 is equal to the letter a. So we're assigning a to this logarithm, comma, logarithm of 3 is b, comma, and logarithm of 5 is c. Okay, so we want to write the following logarithms in terms of a, b, and c. Right? the following logarithms in terms of A, B, and C. Okay, so let's say we want to, A, so that is 2A, example 2A, the logarithm of 10. Okay, can we do that? Sure, using a property of logarithms. This is the same thing as the logarithm of 2 times 5. And then the first property of logarithms says that this is the logarithm of 2 plus the logarithm of 5. Logarithm of 2 is A, according to our problem. Logarithm of 5 is B. No. Logarithm of 5 is C. So erase this guy. C. And that's it. We're done with that problem. Can we do the logarithm of 100 based on this? B. Oh, that's an interesting problem. I just realized something. The base here is 10. So 10 is a little weird because we do know this is equal to 1. So if somebody in this particular example said, oh, the answer is 1, that person would be correct also. That was not the point I was trying to make. You know what? Let me change the problem so that the answer is not that obvious. Let's just put a weird number. Well, not too weird, but something like 7. 7. So I wanted to avoid putting the indexes, but if we don't put the indexes, then we could have some controversy as far as what the answer should be. So if we just left it along with logarithm base 10, well, the logarithm base 10 of 10 is 1. So somebody could just say the answer is 1. Why are you bothering with A and B and C? Well, because I want to practice the properties of logarithms. So that's why we want to change the base so that now it's clear we don't know what we're going to get. But nonetheless, we can still write the answer in terms of A, B, and C. Okay, so logarithm base 7 of 100. And that's what made me think about it, because if we had the logarithm base 10 of 100, the answer is 2. But that's not the point of this. The point of this particular problem is to practice the properties. Okay, so 100 can be written as 2 times 2 times, so that's 4. Another 2 doesn't go into it. Oh, 5 times 5. 5 times 5. Let's write it as logarithm in base 7 of 2 squared times 5 squared. There we go. So that is, now we can apply property number 1. And there's a few different ways to go about getting this logarithm base 7 of 2 squared plus, look, I ran out of room here, so logarithm base 7 of 5 squared. Okay, so those two are together, equals, okay, so now the 2 moves to the front as an x, as a coefficient, so 2 times logarithm base 7 of 2, plus, likewise, see the 2 moves using property 3 of exponents. Where was I? Oh yeah, 2 times the logarithm base 2 of 5. But now this logarithm is just a number. What number is it? We call it right now A, and this number, we call it right now C. So we have 2A plus 2C. And that's it. And the same thing happens with exponents. Rather, with any other kinds of roots. Okay. Oh, by the way, some students could have said, well, isn't this the logarithm of 2 plus the logarithm of 2 plus the logarithm of 5 plus the logarithm of 5? Yes, it is. The two logarithms together can be consolidated into two of the same and two of those. So there's many ways to go about this. Somebody else could say, wait a minute, can we just put 10 squared, because we already have the 10, so that is a plus c, quantity squared, and the squared moves to the front. So this is really 2 times a plus c. And the answer is, sure, we could do that. Yeah. So there's many routes, many ways to get to the same answer, and they will be valid. Just make sure we don't violate the rules. So if somebody said, oh, that is from here, that is logarithm of 2 quantity squared, that would be wrong, because that's not how logarithms work. Okay, so let's practice a few other ones. We want to expand. So this is a different kind of problem. Expand into simple logarithms. Let's say we have the logarithm 3 times the square root of x over y cubed. Okay, so there's a few things going on here. We have a multiplication and a division. This, technically speaking, takes several steps because we have to split this into a subtraction because of the division. Then we split this into a multiplication because, so we would be applying property number 2, property number 1, and then change the square root into an exponent, and then we would be applying that to property number 3. Oftentimes, instead of dwelling on the single properties one by one, we do this in one shot. And I think it's better to practice doing this in one shot instead of several of them. So multiplying means adding. So we have the logarithm 3 plus logarithm x, but this is a half, which goes down as a factor, half logarithm x. Dividing means subtract y cubed. So the cube moves to the front, and then we have logarithm of y. Yeah. So again, I'm trying not to write too many steps, and I'm trying to apply the properties of logarithms one by one. All right. Example 4. Natural logarithm of x plus y square root of z over v w cubed. Okay, now we want to expand into very simple logarithms. Very, very simple logarithms, as simple as possible. We have a product. So this is the natural logarithm of x plus y. Product means plus. Exponent means write the exponent as a factor, natural logarithm of z. Division means the denominator is subtracted, minus natural logarithm of v. And then we have another factor, so we subtract. I ran out of room, so I'm going to write the next term underneath, minus exponent. We can rewrite it as a factor, natural logarithm of w. Some students will ask, wait a minute, we have a product, shouldn't it be plus? You are correct, it should be plus initially, but the whole thing is in the denominator. So we're subtracting an addition, and if we distribute the plus into the two, the negatives will, I'm sorry, if we distribute the negative corresponding to the division to the denominator, then the negative will distribute over those two. Even though initially those two had a plus in between, again, because the whole thing is in the denominator, and we distribute the negative corresponding to that denominator, those two negatives do show up. So again, I try to do this in one shot. Oh, the other thing to remember is we cannot split that up. That addition or subtract, if there was a subtraction, any addition or subtraction is there. We're stuck with it forever. We cannot really, I mean, we can force it if we try to factor out an x, but that really sort of unnecessarily complicates things. So we just leave it alone. 5. Oh, something as simple as the natural logarithm of the quantity x minus y squared would be 2 natural logarithm of the quantity x, minus y, not plus y. And that's it. There's nothing else we can do. Anytime you have a plus or a minus inside of a logarithm, we're stuck with it. Don't even try. It's just going to be not fruitful to do anything with it. The other kind of example is to consolidate back together. So if we give you this problem, put it back together as one logarithm. That's the other kind of problem that I can think of this. Let me remind you before we move on to equations of other properties that are very, very simple. So more properties that are simple. For instance, the logarithm in any base of the number 1 is equal to 0, because any base to the 0 equals 1. Logarithm in base b of b is equal to 1, because b to the 1 equals b. Logarithm in base b of b to the x equals x. Those two operations undo each other. B to the logarithm in base b of x equals x. Please make sure you remember the basic properties. Can you function without knowing them by heart or having them available, at the drop of a hat, just knowing them? Yes, we may be able to function, but it slows the process too much. There's a point after which if we slow a process too much, then the slowness, the speed interferes with our work. So we don't want to slow things too much, because then we have interference. Okay, we're going to start now by solving equations. Okay, and there are different kinds of equations. Let's start with exponential equations with the same base. Exponential equations with same base. Okay. Looking back to see what example number is next. Looks like 6. So we can refer back to those. Okay. Easy problem. 7 to the x equals 7 to the 5. What is x? Don't overthink it. The answer is 5, comma, x equals 5. If we have exactly, identically the same base, nothing else next to it, then the answer is, as in this case, 5. No problem. 7. what if we have 7 to the x plus 9 equals 7 to the 5? Well, that's almost as easy. Okay, first of all, this was super duper easy, almost too easy. Exponential functions are invariable functions, one-to-one, and consequently the outputs are and the inputs are faithful to each other. What I mean by that is whatever the input is has to be the same. It cannot be a different input for the same output. So x has to be 5. Likewise here, the outputs, well, the inputs have to be the same. What happens is that this input is more complicated than that one. So what we say after this, what we imply from this is that x plus 9 has to be 5, and that means that x has to be -4. X equals -4. All right, so let's box the final solution. Okay, 8. What if we have 7 to the 2x plus 9 equals 7 to the 5? Well, I cannot fool you. That just means that 2x plus 9 equals 5. Those are different problems, by the way. They're not the same problem, completely different problems. What I'm doing is building up the complexity of the problems by changing the exponents. And so we move, now I apply some algebra, so 2x has to be -4, which means x has to be -2. And there we have it. All right, let's complicate things even more with example number 9. What if we have 7 to the 2x plus 9 equals 7 to the x? So now, instead of 5, this one is going to stay this complicated, but now this one is not. Okay. The first conclusion is that 2x plus 9 equals x. We can subtract x from both sides. X plus 9 equals 0, which means x equals -9. There we go. Okay, 10. Okay, now let's complicate this even more. You're probably going to think, oh, he's going to do, like a 3x minus 1. Yes, you're right. I'm going to do that. 2x plus 9 equals 7, 3x minus 1. And see what happens. Okay, so the initial conclusion is that 2x plus 9 equals, I shouldn't have done this. This is almost too easy. So I'm going to move the 2x over here by subtraction. So we end up with x. And then add the 1, so 10. There we have it. X has to be 10. Okay. 11. Now let's make it a little more deceiving. 7 to the, okay, x equals 49. Okay, so now things don't seem so obvious as in example 6. Because in all of these examples, you almost got to think this is way too easy. Hey, all just do is drop this 7 and it's almost too easy. It's algebra 1 kind of issue. But wait a minute, this is a 49. I cannot just drop this. There's no 7. Okay, so how do we handle this? Well, there's a 7 hidden in the 49, of course. This is the same as, so we think, oh, this is 7 squared. Now we have the same 7. So the answer is 2, of course, because the exponents have to be the same. But we have to do this step. 12. What about 7 to the x equals 1 over 49? Whoa. Whoa, whoa. So again, we have to think, how can I rewrite this as a 7 with an exponent? Well, 49 is 7 squared, but because we have the reciprocal, we have to subtract. So now we have x equals -2. So the problem was still easy once we learned, or once we wrote this expression, this right side as a 7 to an exponent. Okay. 13. What about 7 to the x equals 49 to the 2x plus 9? Okay, so again, we think of the 49 as 7 squared. 7 squared is the 49. On top of that, we have the 2x plus 9, which means we have to multiply the exponents. If you forgot your rules for exponents, review them. It should take you only a few minutes. And so we have 7 to the 4x plus 18. We multiply the exponents. We don't add the exponents. If we were not thinking straight, we would be thinking that the answer is 2x plus 11, just by adding the two. But no. We got to multiply the exponents. Okay, once we have the two matching sevens, we're good. Then we can arrive to the conclusion that x equals 4x plus 18. And then, 3x. I'm going to do two things at once. I hope you're okay with that. I'm going to subtract the x while I'm going to subtract the 18 from both sides of the equation. And so x has to be negative 6. And there is our solution, negative 6. 14. Okay, so here is the first big, huge, giant problem. 3, I should have put 7, but that's all right, equals 2 to the x. You know what? I'm going to put 7 just because I want to stay with 7. 7, 7, 7. Okay, 7 equals 2 to the x. Okay, we got an issue. We got a problem. Don't have 7. This is, see, when we did 49, that was actually, there was a 7 hidden in the 49 because 7 times 7 is 49. Here, there's no hidden 7. And if it is, actually there is, but it's too deep. It's not obvious. It's not clear. It's not natural. It's kind of unnatural to get a 7 out of that. What we have to do in this case is change, and there's no other way. We got to use logarithms. No other way. We have to, I can start thinking, well, what number as an exponent gives us the 7? I know it has to be less than 3, more than 2, because 2 squared equals 4. That's low compared to the 7. 2 cubed is 8. That's high. So the x has to be between 2 and 3. Again, 2 squared, 2 to the 2 is 4, low. 2 cubed is 8. 2 times 2 times 2 times 2 is 8, high. So the answer is between 2 and 3. Probably closer to the 3 because the 8 is closer to the 7. We have to change this into a logarithmical equation. I hope you remember, that was, I think, in the last video, or one of the last videos, how to change that into a logarithmic equation. So the base is 2. That means that the logarithm in base 2 of the 7 is equal to x. So we have the answer at once. There is the answer. But it requires logarithms. If the bases don't match, we have to use logarithms. If the bases match, we could use logarithms, or we don't have to use logarithms. But the expectation is that students should use no logarithms if the bases match in a fairly natural way, even if it doesn't seem at first that they should match. Like 2 and 8 do match, 2 and 64, 3 and 27 are the same base. 3 cubed is 27. So if there is a natural whole number power that gives the other number, then we're okay. But if not, such as in this case, 2 and 7 do not belong to the same family of powers, natural powers, then we have to use logarithms. So that is the exact answer. This This is what we call exact, not to be confused with a decimal answer. Now, if we wanted to figure this out with a calculator, we would have to do, my calculator, you may have it, but I don't know where it is. The calculator does not seem to have a logarithm in base 2. I think some modern calculators may have it, more modern than mine, but mine doesn't. So I have to use the change of base formula. This is the same thing as the natural logarithm of 7 over the natural logarithm of 2. That is also exact. Those two are exact. Yep, I'm just kind of double checking in my head. Yep, natural logarithm of 7. So we do natural logarithm of 7, close the parenthesis, divide by natural logarithm of 2, close parenthesis, and we have an answer. Let me see it a little more closely. Yeah, about 2.8. So there's the answer, about 2.8. So 2.8, which is, as I mentioned earlier, somewhat close to 3. Now, this is an approximation. Even if you put down all the decimals in the calculator, it is still going to be an approximation because this answer is going to have an infinite number of decimals, and they're not going to cycle. It is not going to give us a nice, a fraction, for instance. So that is an approximation. Even if we put down all the decimals, nonetheless, that's why I'm changing the equal into an approximation to the answer. Yeah. But we still have a good answer, and we can put as many decimals. Once we have about 4 or 5 decimals, that answer becomes quite accurate. If we were talking about money or something like that, we will be you can get close to a penny. The difference will be less than a penny, in which case there's no difference for practical purposes. So virtually, we can get to an answer that is really good by just using enough decimals. That is not a problem. In mathematics, however, see, in a practical sort of engineering way, or chemical way, there is significant digits. And one of the first question engineers ask is, okay, what is my tolerance? How far do you want me to go? And then they work on that. Math people are different. We think, okay, what is the exact answer? And then what is the approximation? We make a big deal about the difference between the exact answer and the approximation. Yep. Yeah. So we emphasize different things. And then this can get even worse. Because we could have example 15. All right. Let's say we have 7 to the x plus 1 equals 2. Let's keep things reasonably simple, to the x. That is already a very complicated problem, but a problem that students are expected to figure out. So we have exponents on both ends, and what makes things really, really complicated is the fact that the bases are not naturally one part of the other. We cannot extract a 7 out of this. We cannot extract a 2 out of that. We have to use logarithms. Now, there is about at least three different ways to do this. Let me show you the way I do it, and then a way other people may be thinking of doing this. I'm pausing. I'm hesitating for a moment because I neglected to mention one thing here. Remember how we got this number by using natural logarithm? Somebody could ask, why did you use natural logarithm? Why didn't you use logarithm in base 10? If I use logarithm in base 10, it will work. It will be just as good. So, logarithm let me do the logarithm of 7, close bracket, divide by logarithm of 2, close bracket. And we end up with, let me double check real quick. Yeah, exactly the same answer. So logarithm or natural logarithm, as long as we're consistent and we use exactly the same logarithm, gives us exactly the same answer. So you can still ask, why did you use natural logarithm and not logarithm in base 10? And the answer is very simple. Logarithm, natural logarithm uses 2 letters. Logarithm in base 10 uses 3 letters, L-O-G. So I rather write 2 letters over 3 letters. That is the reason why I'm using natural logarithm. Just because there's fewer letters when I write natural logarithm, ln, as opposed to log, that's it. There is nothing weird or fancy or extravagant about using one over the other. It's very, very practical. The reason is very practical. So I'm going to do that here. I'm going to use the natural logarithm. So one way to solve this, there's about 3 ways, basic ways, probably even more. One way, so let me show you one way to do this, is to find the natural logarithm, to apply the natural logarithm on both sides of the equation. So we end up with natural logarithm of 7x plus 1 is the exponent equals natural logarithm of 2 to the x. See, solving for x is not easy when we have the x as exponents. It's not like we can multiply or divide or subtract or add. We cannot. We have to use logarithms, because then property number 3 of logarithms, of the properties we started out this video, says that we can put this as a factor and no longer as an exponent. So now we have the quantity x plus 1, we have to put parentheses, times the natural logarithm of 7 equals x. I don't have to put parentheses around the x because it's just one thing, times the natural logarithm of 2. Now, don't be intimidated when you see natural logarithm of 7. It's just a number like 3, like 5, like 7. It's just a number. It looks really weird, but it is just a number. Now we're solving for x. You know, let me give you a quick analogy. Let's say this was, I don't know, 5 and 3. If we had x plus 1 times 5 equals x equals 3. I'm just giving you an analogy. I'm not saying that this equation is the same as that equation. I'm not saying that. But it has the same setup. X plus 1 times a number, x times a number. X plus 1 times a number, x times a number. So there's a times here. How do you solve that? Well, you distribute, 5x plus 5 equals 3x, and then you subtract. So 5x minus 3x is 2x. And then while we do that, we can move the 5 over. So I'm kind of going upward instead of downward. Equals negative 5. And the last thing we do is say, well, x has to be negative 5 over 2. We divide by 2. Okay, so please remember this equation. 5 times x plus 1 equals x times 3. Distribute the 5. Subtract. Subtract the 3x. While we do that, move the constant to the other side, the no x element to the other side. If there's anything to factor, we would factor it, but then we divide. Well, that's kind of what we're doing here. We're going to distribute. See, the first thing we did is distribute the 5. So we're going to distribute this number. Natural logarithm, well, x times natural logarithm of 7 plus natural logarithm of 7 times 1. The numbers just look really awkward. But again, don't be intimidated. Don't be confused by the way a number looks like. If it looks awkward or different, well, it is still a number. If it looks different, it is still just a number. Yeah, there is nothing to It's not a simple number, yeah, but that doesn't mean there's anything wrong with that. Okay, so remember what we did here. We moved um, the 5 to the other side. So this is kind of like the 5. No x, that goes to the other side. This guy goes to this side. So we still have x natural logarithm of 7 minus x natural logarithm of 2. Oops, x times natural logarithm of 2. Sorry, that x looks weird. Equals opposite of the natural logarithm of 7. Okay. Now we can factor the x from both of those. So x times natural logarithm of 7 minus natural logarithm of 2 equals negative natural logarithm of 7. What happened here is that when we did, the 5x minus the 3x, we could consolidate and say, well, 5x minus 3x is 2x. Here, I'm leaving them side by side. Instead of doing 7 minus 2, we cannot do that, by the way. Can we consolidate this into one logarithm? Yes, we may, but let's not do that yet. So here, the answer would be, the last thing to do is to divide by x, rather to divide by this coefficient to leave the x alone. So here we end up with negative natural logarithm of 7 over natural logarithm of 7 minus the natural logarithm of 2. And voila, there it is. We're all done with the exact answer. Can we go farther? Yes, we may. We can consolidate those two as the natural logarithm. Yeah, there's a minus. As a natural logarithm of 7/2. So this is negative natural logarithm of 7 over natural logarithm of 7 over 2, and that's it. So that's another way to write the answer. Either one, this or this, I take as good. And those two cannot be simplified. It's not like we can cancel the logarithms. That would be really, really bad to do that. We cannot do that. We cannot cancel the logarithms, because a logarithm is not something that we're multiplying by something else. It is a function that is being applied. Yeah, we got to be very, very careful. This is one way to get the answer. There's another way to get the answer. So 7 to the x plus 1 equals 2 to the x. Another way. Because if you ask around, they're going to say, well, I didn't want to do it that way. Why don't we get rid of the 7 immediately by doing the logarithm in base 7 on both sides of the equation? Sure. So apply logarithm base 7 on both sides. So logarithm base 7 of 7 to the x plus 1 is equal to the logarithm base 7 of 2 to the x. It has to be, we have to be consistent. We cannot have 7 and 2. No. It's just like when you're solving an equation, you add the same number to both sides of the equation. You don't add different numbers to an equation. So likewise here, we apply the logarithm base 7. Now that simplifies this, and we end up with x plus 1. Here, we multiply by the x. We bring the exponent down as x times the logarithm of, logarithm base 7 of 2. Okay, we still have to subtract. We have to consolidate the x's. So move this x to this side of the equation. X minus x logarithm base 7 of 2 equals, while we move the 1 to the other side of the equation, negative 1. Consolidate the x's. So x1, by that what I mean is factor, minus logarithm base 7 of 2 equals negative 1. And then x finally becomes -1 over 1 minus logarithm base 7 of 2. That's the same answer. If you punch this into a calculator, and I invite you to do that in a graphing calculator, and punch this into a graphing calculator, we should end up with the same answer, the same decimal. If you're off by like the very last digit, that should be okay. But we should end up with pretty much the same answer. Practice these equations. As you can tell, those equations are not easy. They're not easy. If I were you, I would start working on those equations right away, because it takes a while to assimilate how to solve those equations, to get used to the properties of logarithms. We're going to do another kind of equation, logarithmic equations. We haven't done logarithmic equations yet. Logarithmic equations. And we're going to start with some easy ones, and then we're going to move on to more complicated ones. There's going to be one twist to logarithmic equations. I was looking to see what example number is next, 16. Okay, let's say you have logarithm base 7 of x equals logarithm base 7 of 2. If you have pure logarithms and nothing else, just pure logarithms of the same base, mind, the same exact base, logarithms are one-to-one or invertible. What that means is that the inputs and the outputs are faithful. That means that there's only one input for every output and one output for every input. To make the long story short, this output, those two outputs are the same because they're equal. And consequently, the corresponding inputs are the same. Just, I don't like to use the word cancel, but cancel that off and you end up with x equals 2. No questions asked, you're done. That's the answer, as long as we check they're the same base. That's it for that problem. That's a very, it looks complicated, but it isn't. The answer is 2. Done deal. Nothing else to think about. Okay, so logarithm base 7 of 2x plus 9 equals logarithm base 7 of, let's put something more complicated, such as 15. Okay, as long as you have pure logarithms with the same base, the inputs have to be exactly the same. Oh, there's one other thing with logarithms. There's a catch, there's a twist. I did mention that. Here, there was no need to trigger the catch, the possible problem we could have. But I'm going to come back to that in a moment. Okay. So let's solve this equation. The equation is that 2x plus 9 equals 15. Move the 9 over. So 2x is 15 minus 9, 6, and that means x equals 3. And that's the solution. I haven't spoken about the catch, but I want to show you one other example before I do that. Logarithm base 7 of 2 minus x equals logarithm base 7 of 15. Okay, so same drill. 2 minus x equals 15. So move the, well, how do we solve this? We can move the 2 over, so negative x equals 13, but that's not x, that's negative x, so x is negative 13, and that is the correct answer. Because if you plug in negative 13 to this equation, 2 minus negative 13 is really 2 plus 13, and that gives us the 15 that is necessary for those two sides to be equal. Okay. Now, with logarithms, there is one twist, one catch about logarithms. So this is an important note about solving logarithmic equations. Mind the domain. Mind the domain of the logarithmic, that is, or the logarithm that shows in the equation. The input has to be positive. Every input of every logarithm must be positive. Not even zero, positive. And you may be thinking, okay, so that means that's wrong. No. That's why I wanted to show this particular example. The x could be negative and there is no problems. We're good. All right. What is important is that when we plug it in here, this input, so this is the whole entire thing, is what I call the input of the logarithm, not to be confused with the input of the function. So this is the input of logarithm. And what is important is that that has to be greater than 0. So we will get to the point where we need to reject an input. But not, we will reject it not because it is negative, but we will have to reject it because when we plug it into here, we end up with a negative number. So be aware of that. We will have what is, we used to call extraneous solutions. And that's kind of what's going on here. We may end up with extraneous solutions. So we have to check every solution. So for logarithms, double check solutions, all solutions. How? By putting them back into the original equation. Because sometimes you have to reject solutions that are not supposed to be there. 19. Let's say you have logarithm base 7 of 2x plus 1 equals 3. Okay. All right. Be aware this is not a logarithm equaling another logarithm. A logarithm not equaling another logarithm. So we cannot just drop the logarithms. There's two ways to go about this. One way is to say, okay, change this into exponential form. Exponential form, which says 7 to the third equals 2x plus 1. 7 to the third, let's do it with a simple calculator. 7 times 7 times 7 equals 343 equals 2x plus 1. After that, the problem becomes very straightforward. Subtract 1, so 342 equals 2x. Divide by 2, and x equals 171. And there we have it. If we put this back into here, we get 171 times 2, that's 242 plus 1 is, no. 171 times 2 is 342. There we go. 342 plus 1 is 343. And logarithm base 7 of 343 is 3. So that checks. Another way to go about this is to force a logarithm here. So logarithm and base 7 of 2x plus 1 should equal to, and then logarithm base 7 of 343 And then the logarithms cancel, and we end up with 2x plus 1 equals 343, which puts us back into here. So we could do it that way also. If we have more than one logarithm, say, example 20, logarithm, I'm going to keep it as logarithm base 10 of x plus logarithm x minus 1 equals logarithm of 7. Okay, I'm going to rewrite it on one line because logarithm x plus logarithm x minus 1 equals logarithm 7. Okay, don't cancel the logarithms. We have to have pure logarithms. Otherwise, it doesn't work. Pure, solid logarithms. Yep, so don't cancel the logarithms as is. By pure, what I meant by that is one logarithm. That's it. And these are two logarithms. Now, we can consolidate that into one logarithm. So we have logarithm of x times x minus 1 equals logarithm of 7. Same base, one logarithm, nothing else. We can simplify x times x minus 1 is equal to 7. Okay? That means that x squared minus x, multiply that, while we bring the 7 over, is equal to 0. I just made this up, so it is not going to have nice solutions. And by nice, I mean they're not going to be like a 5 or a 7 or a nice whole number. And that's okay. We just go through that. So this is a quadratic equation. We may use the quadratic formula because there's no easy way to factor the 7 or the polynomial. So I'm going to use the quadratic formula. X equals 1 plus or minus the square root of 1 plus, because of this negative, 4 times AC. I'm using the classic formula, negative b plus minus the square root of b squared minus 4 times AC, all of that over 2a. So that is 28, all of that over 2. So we end up with 1 plus or minus the square root of 29, all of that over 2. So we got two solutions. One of them is 1 minus the square root of 29 over 2. And the other solution is 1 plus the square root of 29 over 2. We have to reject this answer. Why? Square root of 29 is 5 and change. 1 minus 5 and change is negative 4 and change. Divided by 2 is negative 2 and change. This is a negative number. Now, we're not going to reject this answer because it is negative. So first, let me record negative number. We're going to reject this negative number not because it is negative. We're going to reject it because the domain of this function is all the positive numbers, this particular function. But that varies from function to function, so watch out. So here we got all the positive numbers. This number is negative. It doesn't fit into this particular function, so we're going to reject it. It does not belong to the domain. So we're going to reject. Let me cross reject. Not because it is negative. Remember our example, was it 14? Yeah, 18. That gave us an answer of negative 13, and we did not reject it. I put a smiley face next to it. That means we keep it. Okay, we want to keep this negative 13 because it works. This number doesn't work. This number will be okay because, again, that is about 5 and change, and 1 is 6 and change. Divided by 2, we're going to end up with 3 and change. Even if we take away a 1, we're good. Had that been minus 4, and had we gotten this answer also, then we would still have to reject it even if the number is positive. So we reject numbers on the basis of whether they are part of the domain of the given logarithms or not. So this one we keep, and that is the only solution. That one we have to reject. Before we close this video, I remember that I didn't show you something. If we had 7 to the x equals, well, let's put plus 2, equals, let's put a 49 to the x. There we go. This problem is similar to the ones we did before. We got a 7 equals 7 with the powers, cancel the 7s, keep the, the powers the same. Everything will work the same way as some of the earlier examples we did. But I'm going to change this problem. I'm going to multiply by 3. Okay, that is a complication we have not seen before. We cannot really do this. This is not what I call a pure 7 with a pure 7. I mean, you could say, well, this is 3 times 7x plus 2 equals 7 squared. And then on top of that x, we have 2x. And can we just continue that way? The answer is no. No way. It won't. It's jammed. This 3 jams the whole equation. Can we solve it? Absolutely yes. In fact, the way I'm thinking of solving this is an interesting example. We might have to come up with a sort of clever way to do this. I'm thinking we can divide by 7 to the x plus 2. So 3 is equal to 7 to the 2x over 7 to the x plus 2. And you guys know how to do the division. We subtract the exponent. So 2x minus x minus 2. Okay. And that is equal to 7. 2x minus x is x. And keep the minus 2. Okay, so we have 3 equals that. Different bases. We have to do logarithms now. I choose natural logarithm of 3. That's the shortest way to write down a logarithm. There's nothing in particular fancy, or there's no esoteric, reason why I'm choosing natural logarithm. It's very, very practical. 2 letters versus 3 letters, or even more letters. I'm going to do 2 steps at once. I'm doing the natural logarithm of the 7 to the x minus 2, but the x minus 2 hops down. So then we can divide by the natural logarithm of 7. So x minus 2, equals natural logarithm of 3, divide by natural logarithm of 7. And then we can simply add 2 to both sides of the equation. So x equals natural logarithm of 3 over natural logarithm of 7, and then add 2, and there we have it. Yeah. So if you don't have a pure 7, as this 3 is messing things up, then you have to figure out how to twist that into something that has fewer parts to it, so that then we can apply same kind of method we did earlier. I don't, I was going to say right now, I don't think this is easy, but again, the concept of easy and difficult is relative. It is very, very relative. Initially, this is not easy. We have to practice. We have to do problems after problems after problems. And then things just start clicking. They start making sense. But this requires a large effort in our part to master, to an acceptable level, solving equations with exponents and logarithms, do not neglect to do problems. Some students are overconfident and they they catch things quickly and they understand things very quickly. But if we don't practice, we will make a lot of mistakes and we will slow ourselves down dramatically, to the point where it really causes issues and problems. Um, yeah. So there's no pill to take. There is no shortcut. We just have to work everything out. Um, yeah. So we'll stop the video here.